Hello ladies and gentlemen, and welcome to Mr. Saucedo's chemistry class. This is going to be our lesson on a brief history of the atom. We're going to be going through some major discoveries and two major experiments that led to what we know as the atom today. So please follow along with your notes and make sure to fill in everything as you see. So we've got to go way back. If we're going to start with the history of the atom, we got to go all the way back to the Greek philosophers in about 400 BCE or about 300 BCE. And so, as far as we know, they are the very first people to write down ideas about atoms and elements. The first person to use the term atom is a Greek philosopher named Democritus, and so he had an idea that the universe is made up of these tiny unbreakable particles that he called atoms. Now, the word atom itself actually comes from a combination of two different things, the word a and then tome. Tome means to cut, and if you put an A in front of it, it's like anti, so it literally means indivisible. So in writing, at least, as far as we know, Democritus is the first person to define what he thought atoms would be. Now, it was popular thought at the time that the universe was actually made up of four different types of things, and so he just thought that there are four different types of atoms, and we call those elements. Now, the elements that they thought there were are fire, earth, water, and air. Anyone who's ever played, sort of any RPG video game kind of knows that. But the word element itself comes from the word elementum, which means first substance. So in summary, Greek philosophers thought that there were tiny unbreakable particles that were called atoms, and everything in the universe was made up of these atoms. They knew that there were at least four different elements, and these elements were different because they had different geometric shapes. Now, obviously, they didn't have any proof of this, but this is sort of what they thought. So we have this, that is the shape of fire, that's the shape of earth, that's the shape of air, and that's the shape of water. And so this was our first atomic theory. Now we're going to jump forward almost 2,000 years and go to the Middle Ages, around the 1300s. Now, at that time, we had a group of scientists that sort of formed the basis of what we think of chemistry kind of today, and they're called alchemists. The word chemist actually comes from the word alchemist. As you can see, it's right there in the middle. And they were obsessed with a couple of things. Primarily, though, they wanted to turn regular metals into gold. So at this point, at least in history, chemistry was really all about making money, and if you ask some chemists today, they probably would say not that much has actually changed. But chemists were actually, or alchemists, sorry, were actually looking at fundamental questions of science at this time, even though they were sort of doing it in a roundabout way of getting rich. So up to this point, though, we now have a list of elements that include things like metals. So we have things like gold and silver, and we have mercury, and we have, all different sorts of other metals out there. And these are now included on the list of elements. So now we're going to jump forward another 500 years and talk about this guy, John Dalton. Now, John Dalton was an accomplished scientist, and he came up with sort of his own theory about atoms and how they work. And so his theory had three main points, and that first point is that all matter was made up of atoms. His second point was that atoms are not created nor destroyed in chemical reactions, they merely rearrange themselves. And his third was that atoms of an element are exactly alike, but they're different from the atoms of other elements. And as we will find out, his first 2 points are entirely true. His third point, though, not exactly. Now, the thing that really bothered Dalton was that he wasn't sure what made elements different from each other. So he knew that there were all of these elements, even though the periodic table didn't really exist now, but he knew that there were all these elements and that they were different from each other. So the way that he liked to think of them are kind of like these billiard balls. And so billiard balls, with just different numbers on them, he just sort of used different symbols to represent them. But he thought that in chemical reactions, atoms, like these billiard balls, kind of collide. And when they collide with one another, this is my example of like a collision, they just kind of stick together. And when they stick together, you now have what we would consider a compound. And then if, another reaction kind of happens, these things can rearrange themselves. And so you might add something new, and you might take away something else. I wonder if I can erase this, but you take away something else, and now you have a new substance or a new compound. And that was his idea of how atoms worked. So this is what Dalton's atom looked like. Every atom was just sort of spherical, so at least we've moved away from the geometric shapes that the Greek philosophers came up with. But that was it. There was nothing in there. It was still an unbreakable, indivisible substance. So John Dalton was in the early 1800s. This guy, J.J. Thompson, was in the late 1800s, and he's actually the very first guy we're going to talk about to win a Nobel Prize. Not the first one ever, but the first one that we're going to talk about that actually won one of these. And so he's the man who is responsible for the discovery of the electron, and it was an insanely important discovery at the time. Why was this such an important discovery? Well, it was the very first time that scientists realized atoms could actually be made up of smaller things. Remember, Dalton is still using Democritus's idea that atoms are indivisible and that they really can't be broken down into other things. So Thompson is the first person to turn this on its head, and it opened up a whole new field of chemistry. And so people decided to see if they could split atoms into smaller bits and really see how they worked and what they were made up of. So I know this is going to look a little overwhelming because there's a lot of stuff on here, but I'm going to describe what Thompson's experiment was. And so what he had is a cathode ray tube, and so that's what this weird picture's of. It's of a cathode ray tube. And here's the thing, he was using two little sheets of metal, which I'm outlining right now in sort of pink, and the idea was he hooked up these pieces of metal to a power source, and he was generating electricity through this sort of tube. Now, this is a vacuum tube, so there's actually no air inside of this tube at all. All of the air has been pumped out. And so what happens when you hook up a battery or something, which I'm going to try to draw very badly here, but there we go. So this would all be connected. And there we go. There's my weird battery thing, and technically I guess this would be connected to that. But when you hook up a battery to pieces of metal in a vacuum tube is you end up getting a weird effect, and that would be that there's this beam of stuff that starts to shoot out. And so I'm drawing that beam right now as a solid blue line. What Thompson was interested in is what is this solid blue line actually made up of? And so I'm going to use little tiny black dots, but this is actually a beam of electrons going across. Now obviously again, no one knew what electrons were, no one knew that atoms were made of smaller things, but what he decided to do is to test what these things were actually made out of, these tiny little, sort of weird beam-like particles that are traveling from one end of the tube to the other. So what he did, which is ingenious here by the way, is he decided to add a magnetic plate. And so this magnetic plate has a positive and a negative part to it. And that's what's sort of, in that picture at the bottom. And make sure, by the way, you label your drawing in your notes. So the thing about this is this negative and positive plate that he added now to the cathode ray tube, well, the electrons in this beam acted a little weird around this magnetic plate, and so these electrons were actually deflected by this plate, and they were attracted, so now I'm going to erase this weird little beam here, they were attracted to the positive part of the plate. So instead of going in a straight line, now they start to go down here. And he even used a magnet to kind of mess around with this. And if you put a magnet around this, the electrons will kind of go either towards or away from different parts of the magnet depending on whether it's sort of a north or a south part of the magnet. And so what he figured out was that there must be these tiny negatively charged particles. And so we ended up calling these later on electrons because we discovered this sort of through electricity. And again, remember, it was deflected by the negative end of the magnet. Now, because of the rules of opposites attracting, he knew that these electrons had to be negatively charged. Not only that, though, he did numerous other experiments, and he realized these things were about 1,000 times lighter than a hydrogen atom. And so they had to be coming from the atoms themselves. And so electrons were discovered, and it was the very first time he realized that there are actually things smaller than an atom. And by the way, Thompson was very intelligent, so he wasn't sure if the identity of the metal that he was using in his plates actually had an effect, and so he decided to retest his experiment with different metals, and he found the same effect every single time, so it didn't matter what metal he used. Not only did it not matter what metal he used, but he always got sort of the same weight for the electron. So he realized that all atoms actually have these tiny little electron things inside of them. The only other logical leap for Thompson to make is that we know that atoms are electrically neutral. So that means that if there are negative particles in them, they also had to have positive parts. Now, he didn't have any idea what these positive particles looked like because he was only seeing a thin beam of electrons. So instead, he liked to think of it as a big blob of positivity. And so sometimes this is called the chocolate chip cookie model of the atom. Now, he called it the plum pudding model, but I like to think of it as the chocolate chip cookie model. So that would be that you have this big doughy blob of positive stuff, and then you have these little tiny chocolate chips, which are the negatively charged electrons that are kind of spread out throughout this positive dough. So this is what Thompson's model of the atom looks like. So again, you have your big blob of positive dough, and you have these little tiny electrons that are spread out. And this was a working model of the atom for a while. Alright, so our next scientist that we have to talk about is called Ernest Rutherford. And so Ernest Rutherford decided to test out whether or not Thomson's atomic model was correct. So he wanted to know if the chocolate chip cookie model was really a good idea for what an atom was like, or if there was a better alternative. And now, when he was doing his experiment, he knew that electrons would probably be so small that they wouldn't really affect his experiment. What he was interested in is, what does that positive blob really look like? So this picture in the lower area is actually what Rutherford's experiment was. And so what he did was he shot alpha particles. Now, it's not important to know what alpha particles are, because we're going to talk about them in this unit anyway. But alpha particles are positively charged, okay? And he had a very thin piece of gold foil. And so this very thin piece of gold foil, he was going to sort of bombard or shoot these positively charged alpha particles and see sort of what happened. Now, how is he going to see what happens when these things are microscopic? I mean, you can't even see an atom now, so how are we going to be able to see it then? Well, he surrounded his experiment in what I'm calling a shooting range. And so he had this giant dome with a fluorescent screen. And this fluorescent screen would light up every time a particle hit it. So you'd be able to actually see a flash of light when an alpha particle came into contact with the foil itself. And by the foil, I mean, the fluorescent screen, not the foil. Now, seeing where this positive scattering of alpha particles would give Rutherford a clue as to what this positive part of the atom actually looks like. So if J.J. Thomson was correct, then this positive blob would be so large and so diffuse and weak that alpha particles should just cut through this like a shotgun blasting through butter. And that's actually sort of the way I like to think about it. So this right here was the expected result, that alpha particles would go straight through and that there'd be no deflection at all. Now, instead, what Rutherford got was this. So most of the particles went through undisturbed, as you can see over here. So most of them went through. But some of them were deflected in crazy ways. So what the heck was going on in the atom to deflect these positively charged alpha particles? It was a big question. So the reveal was that there had to be some centralized positive part that was so positive it was deflecting these other positive alpha particles. So the same way that J.J. Thomson was able to figure out that electrons were negative because they were attracted to a positive plate and deflected by a negative plate, Rutherford was able to figure out that the center of the atom must be positive because it was deflecting these positive alpha particles. The best way that Rutherford could think to explain this was that an atom is actually mostly made up of empty space. That explains why, in his experiment, most of the alpha particles went straight through. Because if it was empty space, then there would be nothing to hit. And instead of just being, empty, there had to be a very, very small positively charged center, though, that would explain why, when a positive particle came near it, it immediately was deflected away. And so Rutherford discovered the nucleus of the atom. It was later discovered that the nucleus of the atom, this very positively charged center, is made up of a group of particles called protons. So now we have Rutherford's model of the atom, and it looks something like this. So there's lots of empty space. Electrons are sort of orbiting around, not getting in the way. And right here in the center, we have our positively charged nucleus. Now, our final scientist, and it gets a little complicated, so we're not really going to talk about his experiment, is named James Chadwick. And so, in the mid-1900s, Chadwick discovered that there are actually neutral particles inside of the nucleus of the atom, and it really was the last missing piece of the standard model of the atom. And yes, Chadwick, in addition to both J.J. Thompson and Rutherford, won a Nobel Prize for this. So now we know that atoms are made up of protons, which are positively charged, neutrons, which are neutral, and by the way, they were the most difficult ones to discover. Obviously, it's kind of hard to discover something neutrally charged, and electrons, which were discovered by J.J. Thompson, which are negative. So our standard model of the atom actually looks like this. We have a nucleus in the middle, which is made up of both neutrons and protons, which again have positive and neutral charges. And then you have electrons, which are still little tiny negatively charged things that are whizzing around the outside in orbits.